All right. Hey, everybody. Welcome back. In this video, we are going to introduce two new tests for convergence, the so-called comparison test and the limit comparison test. And our whole goal here is to be able to sort of identify what they are and explain how we can use them. So let's get into it. Okay, so first up, we have the comparison test. And maybe I should start by saying both of these tests, the comparison and the limit comparison, will compare two different series. So we'll always have this setup in which we have two different series. These will be series whose terms are all positive, right? So A sub n and B sub n are the terms in our two different series, and they're both greater than 0. Or I should say all of the terms are greater than 0. So in the comparison test, our setup is as follows. We have our two series. We have that the series A sub n and the series B sub n all have positive terms. And furthermore, we know that A sub n is strictly less than or equal to B sub n. So we have 0 less than or equal to A sub n, less than or equal to B sub n for all elements, all terms in the series. I said here all sequence elements, I mean all terms in the series for large values of n, right? What that means is maybe for the first 2 or 3 elements, maybe A sub n is bigger than B sub n, but once we hit a certain threshold, all future values will have A sub n less than or equal to B sub n. So that's our setup. If we have that ordering between our series A sub n and our series B sub n, then we will know that if B sub n converges, then A sub n will also converge. And if A sub n diverges, then B sub n will also diverge. All right, to try to explain this a little bit, I'm going to draw our two series. So I'm going to draw A sub n in red. I'll draw it down here. So maybe these are my sequence elements. Let's say that. These are my sequence elements, A sub n. And I would add up all of these numbers to get my infinite series. And then in blue, let me go ahead and draw B sub n. So the idea is going to be that B sub n is bigger than A sub n for at least all n values big enough. So I'm going to pretend that the first B sub n is smaller than A sub n, but let's pretend all future elements, so all that are big enough, that are all large values of n, we have B sub n is bigger than A sub n. So maybe B sub n looks like this. They don't all have to be decreasing, right? But we do have that at any given point, A sub, for our larger n values, at any given point, we have A sub n is less than B sub n. And if that is the case, then we can use this comparison test to directly compare our two series. And what I mean by that is, notice the sum, as k goes from 1 to infinity, the sum of B sub n will necessarily be bigger than or equal to A sub n. Maybe ignoring this first point, right? Because the first point doesn't really change anything as far as convergence versus divergence. For the second point onward, every term B sub n is bigger than its corresponding term A sub n. And that's true completely going forward. What that means then is that if the infinite series B sub n converges, that means that adding all of these values up gives us a finite number, then A sub n, where all of these values are necessarily smaller, right, closer to 0, then A sub n will also converge because we're adding up things that are smaller than they were for B sub n, and we already know that B sub n added up to a finite number. Therefore, our A sub n terms will add up to a finite number, and therefore A sub n will converge. On the flip side, if A sub n diverges, that means that I'm adding up all of these smaller numbers, and I'm getting infinitely much area under there, right? So this is a series that is diverging. I should say this diverges to infinity because all of these terms are positive. So if A sub n diverges, then B sub n is adding up even more area, right? All of the B sub n's are bigger, so we're adding up even more numbers. So B sub n will necessarily also diverge to infinity. All right. So that is our comparison test. I'm actually going to skip ahead for a moment, and let's look at an example to determine whether or not 1 over n cubed plus 2n plus 1, whether this series converges or diverges. All right, and so when I look at this, I'm trying to figure out whether this converges or diverges. I might notice that because this is a polynomial, right, in the denominator, the n cubed plus 2n plus 1, I might try to compare this to the series 1 over n cubed, right? So in other words, I might compare the series up above, 1 over n cubed plus 2n plus 1. I might compare it to the series 1 over n cubed. And what we'll see is for every n, okay, so for each n, we have that 1 over n cubed is specifically going to be bigger than 1 over n cubed plus 2n plus 1, right? Notice this is true. This is true because the denominator, n cubed plus 2n plus 1, is bigger than the denominator that's just n cubed for any value of n, right? So this denominator will be bigger, therefore the whole fraction will be smaller than that whole fraction. So for each n, we have that comparison, and we already know that this series converges, right? Why do we know that? Well, this was a p-series. 1 over n cubed is a p-series, p equals 3, and because that p-value was bigger than 1, it converged. So sort of summarizing what we have, we know, take a moment to write this out, we know that the sum 1 over n cubed converges. And that's true because that was a p-series with p equal to 3. And so therefore, we know that this new sum, 1 over n cubed plus 2n plus 1, will also converge. And that's true by this comparison test. Awesome. All right, great. Now, the key idea behind the comparison test was that we had these two series and we were able to compare their sums. The limit comparison test works similarly, except instead of comparing the total sums, we are going to compare the limit of a ratio of terms. So let's read through this. So we have, again, our two series, a sub n and b sub n. A sub n and b sub n are each positive sequences. The individual terms form positive sequences. And positive, again, just meaning that all of the a sub n's and all of the b sub n's are bigger than 0. And so in this case, we will consider the following limit. The limit as n goes to infinity of these ratios of the form a sub n over b sub n. So a sub n is a sequence, right? I should say, this is a series, but the individual a sub n's form a sequence. The individual b sub n's form a sequence. And so a sub n divided by b sub n, that ratio forms a sequence. We have a sub 1 over b sub 1, a sub 2 over b sub 2, and so on and so on. And we can simply take the limit as n goes to infinity of this sequence of ratios. And if that converges to a limit, then we have the following 3 bullet points. If that limit is a positive but finite number, then both a sub n and b sub n, they either both converge or they both diverge, right? And one will converge if and only if the other converges. So if that limit L is a finite positive number, then a sub n and b sub n will either both converge or both diverge. If L goes to infinity, right? If L is equal to infinity, that means that the a sub n's are staying far bigger than the b sub n's. And that will mean that if a sub n the series converges, then B sub n, the series, will also converge. Finally, if L equals 0, if that limit actually equals 0, that means that the A sub n's are getting smaller considerably faster than the B sub n's, right? That's what would make this limit tend towards 0. And so therefore, if B sub n converges, right, then A sub n, which is considerably smaller, whose terms are considerably smaller, will also converge. So we have this slightly more complicated limit comparison test that lets us determine whether or not our corresponding sequences converge depending on the value L, that is the limit of this ratio. All right, that's all I got for this video, but I will see you all next time.